In this tutorial we're looking at section 13.6 on projectile motion. Okay, so we'll go through a bit of the information that we know, okay, or that we're told about. Okay, so we've got a little picture here that kind of sums up what we're talking about. Okay, so we've got our x and y direction. Okay, so our j and I direction for our vectors. Our vector has initial velocity v, acting at an angle theta to the horizontal. We get a maximum height, which is capital H. We have a range, which is capital R. And we know that we have acceleration due to gravity G acting down all the time. So our v meters per second is our initial velocity. Our alpha degrees is our angle of launch. Capital T is our time of flight. Okay, so we also get our H is our maximum height. R is our range. We can say x equals x to t is our horizontal displacement, and our y of y to t is our vertical displacement. Okay, and we know that our time is between 0 and our big T, which is our time of flight. Okay, so we just got a couple of things to remember. Our position vector is given by r of t equals x of ti plus y of tj. Our velocity vector is the derivative of our position vector, and it's r dot of t equals x dot of ti plus y dot of tj. Our acceleration vector is our derivative of our velocity vector, and that's r double dot I equals x double dot ti plus y double dot tj. The only force that acts on the projectile is the weight force. Okay, so we say G is equal to negative GI because it acts down, and we say G is 9.8 meters per second squared. Okay, so that means our acceleration is equal to negative GI. Okay, our velocity is equal to negative GTI plus C1, and our R of naught equals our V cos of alpha I plus V of sine of alpha j, so that's our initial velocity vector. We say that our position vector, okay, R of t is given by Vt cos of alpha I plus Vt sine of alpha minus a half GT squared, j plus C2. Since the projectile starts at the origin, okay, we can say that C2 is 0. Okay, but if the projectile is fired from a height h, then C2 is going to equal hj. Okay, we've got a bit more theory to go through yet. Okay, our time of our flight, our capital T, is equal to 2v sine alpha on g. Our range of our flight is r equals v squared sine of 2 alpha on g. And our maximum range occurs when alpha is 45 degrees. Our maximum, sorry, I've got flight there, but that should be height. Our maximum, our maximum height, h equals v squared sine squared alpha on 2g. If an object is fired from a height of h meters, then the maximum height becomes h equals v squared sine squared alpha on 2g plus h. Hey. We've got a bit of a section on improving the range. If the object is fired from some height h, okay, then we can solve the parametric equations x of t equals vt cos alpha and y of t equals h plus vt sine alpha minus a half gt squared to find the time of the flight and the range. Okay, because our time is, when we look at our t, okay, and our height is our h, okay, and those type of things. So the equation of the path, okay, is given by y equals x tan alpha minus gx squared sec squared alpha on 2v squared. Okay, and this is actually the equation of a parabola because we've got our x term, okay, our tan alpha, that's just a value, g is our 9.8, okay, sec squared alpha, just a number, and 2v squared is just a number. Okay, we can also find the angle of our projection, okay, using g of x squared on 2v squared tan squared alpha minus x tan alpha plus y plus g of x squared on 2 times v squared equals 0. Okay, so I just want to check one thing very quickly there, because I'm just worried that I might have written down something a little incorrectly there. Let me just double check. Oh, that's correct. Okay, and the point, so what we need is this equation. Okay, and we'd also need a point xy that our particle passes through. Okay, so we get these values. And we'd also need an initial speed, so we've got v, we know g. Okay, that way everything, all our unknowns given to us apart from our value of alpha then. Okay, so we could find our angle. Okay, we'll have a look at some worked examples. Now, just before I get into the worked examples, okay, if you're studying physics, okay, you know that we've actually done projectile motion there, okay, and I would strongly recommend that you use some of those skills whenever possible, okay, because as you've seen, some of these equations aren't very nice, okay. However, if we use just our constant acceleration formulas, okay, then we can solve a lot of these problems without the need of all the vectors, okay. Of course, that means that we perhaps aren't getting as skilled and practiced at using some of these equations, and we may need to use them in an assessment situation. So there is that balancing act there. So we'll have a look at worked example 13. So we're told a golf ball is hit off the ground at an angle of 53.13 degrees. Okay, that's going to equal our alpha value, with initial speed of 25 meters a second. Okay, we're asked to find the time of our flight. Okay, well, t equals 2v sine of alpha, okay, over g. Well, we know then, well, t equals 2 times our velocity, which is 25, okay, times sine of our 53.13, all over our acceleration due to gravity, which is 9.8. Okay, so our t is going to equal 4.08 seconds. Okay, we're also asked to find the range. Okay, so we can use our r equals our v squared sine of 2 alpha over our g. So that means we have 25 squared sine of 2 times our 53.13 over our 9.8. Okay, so we get then a distance of 61.22 meters. Okay, when we calculate that. And the last part is to find our maximum height reached. So h equals our v squared sine squared alpha over 2g. Okay, again we can put in our values, so our 25 squared sine squared of our 53.13, right, over our 2 times 9.8. Okay, when we calculate that, we get a height of 20.41 meters. Okay, that's all we've got for our first worked example. Okay, worked example 14. Okay, a boy throws a ball from the top of a hill 2 meters above ground level, okay, with initial speed of 10 meters a second at an angle of 40 degrees to the horizontal. So what we've got, okay, is got some height here of 2 meters. Okay, and come off like this. Okay, we've got our 10 meters a second at an angle of 40 degrees. Okay, so that's the situation we have. Okay, we need to find the time of the flight and the horizontal distance travelled to start off with. Okay, so what we need to do here, okay, is we know our v equals 10 and our alpha equals 40. Okay, so we need to be thinking, well, our acceleration, our r of t is equal to negative 9.8 j. Okay, and we also need to look at our initial velocity vector. Okay, well, in the horizontal direction, then it's going to be 10 cos of 40 I, so that's just breaking into our horizontal component, plus our 10 sine of 40 j in our vertical component. Okay, so we can then say, well, our r t is our 10 cos of 40 I plus our 10 sine of 40 j, okay, minus our 9.8 t j. Okay, at the moment, okay, we also know that since the initial position is 2 meters above the ground, we can say that r naught equals 2j. Okay, so that means then that our r of t okay, is we're going to be our 10t cos of 40 I plus our 2 from our value here, our 2j there, plus our 10t sine of 40, okay, minus our 4.9t squared, okay, j. Okay, so we know that the ball hits the ground when the vertical component is equal to 0. Okay, so we need to set this part equal to 0, because that's our vertical component. Okay, so we need to say, well, our 2 plus 10t sine of 40 minus our 4.9t squared equals 0. Okay, when we solve that, we get values of t equals negative 0.26 and t equals 1.57. So that's just solving this equation for t, which you just do in your calculator. Okay, but we know t has to be larger than 0, okay, because t always starts at 0. Okay, so this would be the time back here when we're at this height. Well, that doesn't make sense. So we ditch that one. Okay, so we've got to go with our t equals our 1.5. Okay, so we can then say, well, how far does it go? Well, we can put our t value into our horizontal component here. Okay, and say, well, we know our x of t is our 10t cos of 40. Okay, so our x of 1.57, do it 10 times 1.57 times cos of 40, which means we get a horizontal distance of 12.04 metres. Okay, so we'll keep moving on. There's a bit more to this worked example. We need to find the maximum height reached. Okay, so what we need to do, okay, is solve our our velocity vector, okay, in our I direction, okay, equal to 0, because at the top of our flight, okay, our velocity vertically is 0. Okay, so I'll just change colours here to make it a bit clearer. So we can say our 10 sine of 40 minus 9.8 t is equal to 0. Okay, so that means that we get t to be a value of 0.656. Okay, now usually you won't really ignore that. Sorry, with these ones, because of the way the path is here, okay, because we're above the origin or above the horizontal where the ball hits, okay, we can't just say that the time is half of what we had. Okay, we could do that if we were at ground height when we had our ball being thrown or whatnot. Okay, so what we do then is look at our position vector, okay, in the y direction, okay, which is this part here, okay, and sub in our t equals 0.656, and say our y of t is equal to our 2 plus our 10t sine of 40 minus 4.9t squared. So we go y of our 656 equals 2 plus our 10 times our 0.656 times sine of 40 minus our 4.9t, 0.656 squared. Okay, and when we do that, okay, we find the maximum height reached is 4.11 metres. Okay. Part C, we want to find the speed and angle at which the ball lands. Okay, so what we need to do, okay, this time, okay, is we know, okay, that it takes 1.57 seconds to hit the ground. Okay, so we need to look at that going into our velocity vector. Okay, so what we can do, actually again, I might just change colours, okay, is we can say our r dot of our 1.57. Okay, and we're using our r dot because we want our velocity vector, okay, when we hit the ground. Okay, well that's going to be equal to 10 cos of 40 I plus our 10 sine of 40 j, okay, minus 9.8 times our 1.57 j. Okay, when we do that, we find that we get a velocity vector that is 7.66 I minus 8.96 j. Okay, so we actually want the speed and the angle. So our speed, remember, is our magnitude of our velocity vector. Okay, so we're just doing pi theta here. Okay, 7.66 squared plus our 8.96 squared under our square root sign. Okay, so that means that we get our speed of 11.8 meters per second. Okay, what we need to do is our angle that we hit the ground. Okay, where you can say that would be theta. Okay, now we know this is our horizontal component and our vertical component. Okay, so we can simply say that theta is equal to inverse tan of our 8.96 over our 7.66. Okay, so theta is going to equal 49.5 degrees. Okay, so we have a velocity of 11, or a speed, sorry, of 11.8 meters per second, and striking an angle of 49.5 degrees. Okay. Part D showed that the ball travels in a parabolic path. Okay, so what we'll do, switch colours again. Okay, and we say, well, we know our x equals our 10t cos of 40. And we know our y equals our 2 plus 10t sine of 40, minus our 4.9 t squared. Okay, so what we do is we rearrange this one for t, and we say, well, t equals our x on 10 cos of 40. Okay, and we're going to sub that t value in for y. Okay, so then we get an equation for y, which is y equals 2 plus 10x sine of 40 over our 10 cos of 40, okay, minus 4.9 outside of x on 10 cos of 40 squared. Okay, and if you actually expand out and that sort of thing and collect our like terms, that type of thing, we can simplify using some, our 10's are going to cancel out, sine over cos is tan, okay, all those type of things. Then we get 2 plus x tan of 40, okay, minus 49 x squared on 1000 sec squared of 40. Okay, and we can see that this is simply a equation of a parabola, okay, where we're in the form y equals z plus bx plus ax squared. Okay, and if you want to, you could always just work out what these numbers are, okay, so you can see it in that form a little bit easier if you'd like. Okay, so we'll move on to the next worked example. Looks like we've got 2 worked examples to go, okay, which is worked example 15. Okay, so for this one, we know a basketballer shoots for goal from the 3-point line. She throws the ball with an initial speed of 15 meters per second. Okay, so we know v equals 15 meters per second. Okay, the ball leaves her hand at a height of 2.1 meters above the ground. Find the possible angles of projection if she is to score a goal. Okay, so here's a little bit more information, but I'll include that in our little picture that we're going to do. Okay, so what we're saying here is we've got a height of 2.1 meters, okay, which is the height that they're releasing the ball at. Okay, the distance, okay, to the 3-point line is 6.25 meters. Okay, and the basketball ring, okay, is at a height of 3.05 meters. We're saying there must be 2 paths, okay, one that goes something like this and one that goes a bit higher. Okay, and we're going to find our angles to the horizontal. Okay, so we know that the basketball must pass through the point 6.25, 3.05. Okay, so it won't be 3.05, 6.25, and 0.95. Now that might seem a little bit odd, okay, but really we can consider this, okay, with our height of 2.1, okay, we could consider that as the horizontal, okay, and then we've just got to get a distance of another 95 centimetres. Okay, so what we need to do, okay, is have a look at finding our angle. Okay, so that equation was our gx squared on 2v squared tan of our alpha minus x tan of our alpha, okay, plus our y plus our g of x squared over 2v squared, okay, equals 0. Okay, and we can sum in what we know. So we know our g is our 9.8, our x squared, okay, is going to be our 6.25 squared over 2 times our velocity is our 15, so times 15 squared, tan of our alpha minus our 6.25 tan of our alpha, okay, plus our y value, which is our 0.95, okay, plus our 9.8 times our x value, which is 6.25 squared over 2 times 15 squared, okay, equals 0. Okay, are we going to do that much more work with this? Okay, probably not. Okay. Sorry, just give me 2 seconds. We seem to have... Yep, sorry, we just had a little typo in the textbook. That first one is tan squared alpha. Okay, sorry. And you'll see that in the worked example, that the first step that they don't have the tan squared. Okay, so we can simplify this. Okay, it's just calculator work. Okay, so you can see there that they've got 0.8507 tan squared alpha. So this value is 0.08507. Sorry, 0.8507. Okay, and our value up here is all this is equal to 1.8007. Okay, so what we find then, okay, is that we can, what we need to do, okay, is realise then that if we were to set up a quadratic here, okay, then we've got our A value is 0.8507, our B value would equal negative 6.25, our C value would equal 1.8007. Okay, so looking at the discriminant, okay, then we get, so remember our discriminant is equal to b squared minus 4ac, okay, and the square root of our will give us a value, okay, of 32.935, okay, and the square root of our discriminant, okay, will be 5.739. Okay, so that means that we can say, well, our tan of our alpha, okay, we can find using an equation, our general quadratic equation of minus b plus or minus the square root of the discriminant over 2a. So we could have done that just using our general quadratic formula from the word go. So that's our negative b, so that's going to be 6.25 plus or minus our 5.739 over our 2 times our 0.8507. Okay, so what we get then, okay, is that alpha, when we work that out, and we'll have to do our inverse tan, of course, we find that we get alpha is equal to 81.92 degrees, or alpha is equal to 16.72 degrees. Okay, so they would have to be the two possibilities, okay, that we could get for our angle, okay, of launch in order to score a goal. Now we've got one more worked example to go, which is worked example 17. Okay, there is worked example 16, which is a little bit of a proof question. Okay, but we'll have a look at worked example 17. Okay, so a shot is thrown by a shot put competitor on ground level. At a time t in seconds measured from the point of release of the shot, the position vector r of t is given by r of t equals 7ti plus 5t plus 6 outside of e to the negative t on 2 minus 1 j, okay, plus 2 plus 12t minus 5t squared k. Now I reckon looking at that you'd be thinking that we're probably getting one of our harder examples that we could be expected to get, given that it's in our 3 dimensions. Okay, so we know I is a unit vector in the east direction, j is a unit vector in the north direction, and k is a unit vector vertically up. The origin O of the coordinate system is at ground level and the displacements are measured in metres. Let P be the point where the shot hits the ground. Find the time taken for the shot to hit the ground. Okay, so the shot will hit the ground when our vertical component has a time equal to 0. So that's simply going to be our 2 plus 12t minus 5t squared that equal 0. Okay, so we can solve using the general quadratic formula or our calculator, whichever we like. We find that t equals negative 0.1565 or t equals 2.5565. Now obviously our time can't be negative, so we're going to ignore that one. Okay, so we know the time that it takes is we just round it to 2 decimal places, 2.56 seconds. Okay, so what looked like a complicated equation, actually to find the time taken for it to hit the ground is reasonably straightforward. Okay, for part B, how far from the origin does the shot hit the ground? Okay, well, what we need to do, okay, is substitute in our t value for time into our position vector. So we're going to say our r of 2.56 okay, is going to equal 7 times 2.56 I, okay, plus we're going to get our 5 times 2.56 plus 6 outside of e to the negative 2.56 on 2, take 1, j, okay, plus we're going to get our 2 plus 12 times 2.56, 8, take 5 times 2.56 squared, now k direction. Okay, so what that gives us, okay, when we actually do all that, okay, running it all through, okay, is that we get 17.895 I plus 8.453 j, okay, which makes perfect sense, okay, that we don't have a k component because we just worked out, well, at this time t equals 2.56, we just found that value setting this part, our k part, okay, equal to 0. So we're not expecting anything there. Okay, so what we need to do though, okay, is we actually need to find the distance. Okay, we haven't actually got that. We need the modulus of our r 2.56. Okay, which is going to be our Pythag, which is 17.895 squared plus our 8.453 squared inside our square root sign. When we do that, it's 19.79 metres. Okay. For part C, we need to find the initial speed of the projectile. Okay, so what we need to do is we need to take our derivative because we need our velocity vector. So our r dot t, well, that's going to be our 7i plus we'll get 5 minus 3e to the negative t on 2 j, okay, taking our derivative here, okay, plus we'll get 12 take 10t k. So we've got our velocity vector now, so we need to let t equal 0, so r dot 0, okay, is going to be 7i, okay, plus we've got 5 minus 3 e to the 0, okay, j, plus we've got 12 k, so that's just going to be 7i, 8 plus 2j, 8 plus 12k. We want the initial speed, so we're going to take the modulus of that, which is just our Pythagoras in 3 dimensions, okay, which gives us a value of 14.04 metres per second. Okay. And we need to find, lastly, we've got to find our speed and angle at which the shot hits the ground. Okay, so what we need to do is we need to substitute in our time of 2.56 into our velocity vector. Okay, that'll give us a nice vector which we can then take the modulus of. Okay, so when we sub in our r dot of our 2.56, okay, we get our 7i, okay, plus our 5 minus our 3e to the negative 2.56 on 2j, okay, plus we get 12 take 10 times 2.56 k direction, okay, which gives us a vector of 7i plus 4.16 j, okay, minus 13.56 k. Find the modulus of that. Again, it's just Pythagoras' theorem, so 7 squared plus 4.16 squared plus negative 13.56 squared, okay, is simply going to give us a value of, okay, for some reason they don't give it in any simpler way, so I guess I do. So that becomes the square root of 250.34, okay, which is a value of 15.82 meters per second. Okay, you just got to look a little bit down the bottom until you find it. Okay, so what we need to do then, okay, is we need to find our angle. Okay, so what we can say then is our tan of our angle, I'm just using theta, okay, is actually found by doing our z of our velocity vector over the square root of our x squared plus our y dot squared, okay, which we can say, well, we know our z is our 13.56 over our square root of our x, which was 7 squared, plus our y, which is our 4.16 squared. Okay, when we do that, okay, then again we've got to do our inverse tan. Okay, so this is going to be tan of theta equals a value of 1.665. So theta equals inverse tan of our 1.665, okay, which gives us a value of 59 degrees 1 second. I'm not sure why they did it in minutes and seconds, but they did. Okay, so we can say that our velocity, our speed is 15.82 meters per second, okay, and hits the ground at an angle of 59 degrees 1 second. Okay, 1 minute, sorry. Okay, so that's the last worked example. Okay, a couple of these have been a little bit trickier, but generally speaking, the process isn't too bad. We've been working with our vectors quite a fair bit, so this is really just an application of that work. So hopefully you'll be able to get through these questions without too much trouble.